Hi everyone, welcome back to your science sketchbook. I've got another review game for you on the topics shown here. Each question will appear on screen for 20 seconds, so feel free to pause to take time to solve it, and then after I show how to find the answer. So let's go. Question 1. How many chiral centers are present? Alright, so when you're checking the chiral centers in a fused bicyclic compound, there are a few different areas to confirm. So, a chiral center is where there is an atom with 4 unique groups attached to it. Let's check out this carbon in pink. So we've got a chlorine, and to the right, a carbon chain, just a couple of CH2s, and then to the left, you immediately have a bridgehead, or CH right there, and of course an implied hydrogen. That's 4 unique groups, so that one is a chiral center. Now, let's not forget about the bridgeheads. So in green here, you've got to the right, close to that carbon, downwards immediately to the other bridgehead, to the left to a longer chain of carbons, just CH2s, and of course the implied hydrogen. Alright, so that one is also a chiral center. On this blue carbon, we have up immediately to the other bridgehead, to the right where you end up kind of closer to the chlorine, and to the left where it's just a carbon chain CH2s, and then the implied hydrogen. So that one is also indeed another chiral center. So that's 3 chiral centers total. Question 2. What is the RS configuration of the indicated chiral center? Alrighty, so this was the same molecule we saw earlier, but now we are seeing that one of those chiral centers had a counterclockwise or S spin. So to find the spin, the first thing you do is rank the 4 groups on that chiral center. You do this by finding the heaviest atomic weight at the first point of difference, or first point of contact. So look, we are comparing the first atoms connected: chlorine, hydrogen, carbon, and carbon. Referencing a periodic table, chlorine is heaviest and hydrogen is lightest. But what is heavier, carbon or carbon? Well, neither, right? So you need a tiebreaker. This is where you move to the next carbon connected. The carbon to the left is immediately bonded to another carbon, just one bond length further, and it is bonded to another carbon downwards, and of course it has its implied hydrogen. So you can make a note, you've got 2 carbons and a hydrogen on that side. To the right, that carbon is immediately bonded to 2 implied hydrogens, and then that other carbon 1 bond length down. So that is 1 carbon and 2 hydrogens. Now we compare. Both groups have 1 carbon that are equal, but the left had an extra carbon. Thus, the left is a higher priority. So to find the spin, hide the atom in back and read the rest in numeric order. 1 to 2, 2 to 3, that looks counterclockwise. But we gotta remember our little trick. After finding the spin, check the back or the dash. If rank 1 or 3 is in the back, you have to flip your answer. We just have 4 in the back, so you can leave it as S, and you're good to go. Question 3. All of the following are true of enantiomers except Alright, so did you make sure to read that question carefully? All are true except that first one. Here is a brief reminder of some conceptual info on enantiomers. First, they have the same physical properties. Next, their rotation of light or optical activity is opposite. Then, they interact with enzymes differently. And finally, they have the same chemical formula. They just have that spatial difference. So they are considered stereoisomers. Here are a couple of ways you can recognize enantiomers as well. They can either be in the same orientation, just flipped wedges and dashes on the chiral center, or they can look like what is considered a non-superposable mirror image. So the whole structure is the same, but in an opposite order. Anything wedged would stay wedged, for example. So aside from these visual indicators that you can look out for, you can always find the RNS configurations and just confirm that they are opposite from one molecule to the other. Question 4. What is the relationship between the two? Okay, so diastereomers. It's all just because of some directional differences. Let's take a look. So in green, we have this methyl in the up position, and in blue, this other methyl in the down position. On the other chair, we have both methyls in the down position. That means the molecule on the left is trans, and the other is cis. Any cis-trans relationship is a diastereomer. Note that neither of these molecules are chiral. So as you can see, you don't need to be chiral to exist as a diastereomer. Just cis and trans is good enough. Question 5. A sample contains 75% of the R and 25% of the S enantiomers. What is the enantiomeric excess of the R enantiomer? All right, did you get it? I don't even have anything to really show here. It's just a simple subtraction. When you don't have a 50-50 split of enantiomers, or racemic mixture, you just subtract the lower value from the higher, and that's how much excess you have. Question 6. What is the configuration of the indicated chiral center? Yep, it's R. Slightly more challenging for finding your ranks, so let's see. Directly off of our chiral center, we are going to compare the first atoms: nitrogen, hydrogen, carbon, and carbon. So nitrogen is heaviest, hydrogen is lightest. Now carbon versus carbon doesn't work, so we move to the next atoms for the tiebreaker. On the left, that carbon is bonded to 3 other carbons. So we have C, C, C. On the right, that carbon is bonded to hydrogen, and with double bonds, just treat the double bond as 2 connections to carbon, because you need to be comparing 3 groups. So it is C, C, H. The one on the left had an extra carbon to outcompete that one hydrogen on the right. So rank 2 is on the left and 3 on the right. Now hide the dash and follow the numbers. Looks like it's clockwise. As always, confirm with the dash. If 1 or 3 is back there, you flip the answer. We have 4 in back, so we're good. Keep it R. Question 7. Is this molecule optically active? Alright, so to be optically active is to be chiral overall. To be chiral, you need to have chiral centers, and you cannot have equal ones that cancel out. Both sides have fluorine, methyl, hydrogen, and that CH2 group coming off their chiral centers. Should one of their spins be R and the other S, this could be what's called a Meso compound. That's a molecule with chiral centers that cancel out and thus makes it achiral overall. So let's rapid fire rank our groups and hide that dash, follow those numbers, and see that it is clockwise R. Same ranks on the other chiral center, hide the dash, and you'll find that the spin is counterclockwise S. They do indeed cancel out. This makes it a meso compound, which is achiral. So to recap, a compound is meso if chiral centers have the same groups on them, and one is R, one is S. This molecule has both features, so it is meso, thus achiral and optically inactive. Question 8. What is the relationship between the two molecules? Okay, wow, time's up right when I clicked on it. Anyway, yes, these are enantiomers. If you recall from question 3, I showed a couple of examples of how to recognize enantiomers. Both have the same chiral center, and they're written in the same orientation, kind of left to right. It's just that the wedge flipped to a dash in one of them. But a more systematic approach is just to check, do they have opposite R and S configurations? Go ahead and find the first one, and you'll see that it is clockwise, so R, and group 4 is on the dash, so no need to flip. For the second one, find the spin as well. And it is going clockwise. It kind of looks like it's going to be R, but look, group 1 is on the dash, so you must flip that answer. It's actually S. They otherwise have all the same atoms connected in the same way, so with those opposite chiral centers, they are indeed enantiomers. Question 9. What is the relationship? Did you get it? For this, I advise checking the chiral centers. You can convert the Newman to bond line if you want, but I'm going to show you how to do it straight from the Newman projection. So, diastereomers need at least one center that is different and at least one that is the same between them. Both the front in red carbon and back in blue carbon are chiral centers. So let's find that spin. Oxygen is rank 1, then the back carbon there, which is bonded to an extra carbon and oxygen, will be our second rank, then methyl, and then hydrogen. Hide what's in back, which is that entire blue carbon there, and just follow the numbers. It is going clockwise. And look, it's just group 2 in the back, so no need to change. It's just R. The groups are the same, and thus so are the ranks for this other front carbon. It's just going counterclockwise instead, so it's S. And again, no flip needed. So far, one is R and one is S. It has the potential to be enantiomers or diastereomers at this point. So let's check the chiral centers on that back carbon. The method will be slightly different. So again, rank 1 to oxygen, now rank 2 will go to the front carbon of the Newman. Now look, here is the difference. I know that this is the front carbon, but we're actually going to hide this one, since it's in the middle and we just kind of want to follow our outer numbers again, right? And besides, where is the dash? Where is the back of the back carbon? So 1, 3, 4, that looks clockwise or R. Now look, we uncover this front carbon, but what for? That is not the back carbon, right? And we only need to check the back if we need to flip. But as I said, where's the back? That entire blue carbon that we're on is the back. So here's the slightly different rule. For the back carbon of a Newman projection, check if both 1 and 3 are in back there together. If so, you flip your answer. That is true here. Both 1 and 3 are back there. So instead of clockwise R, it will switch to S. So the back is S on that one. Let's confirm with the other. On this other back carbon, it seems both 1 and 3 are in the back again together. So this clockwise looking R does have to flip to S. So the back is S for this one as well. Now we can compare. They are not enantiomers because all chiral centers need to be opposite. You go from R to S in front, but stay S and S in back. Since at least one is the same and at least one is different, they are diastereomers. As another perspective, you can almost consider the chiral centers on the left to be trans to each other, and now they are cis to each other on the right. Again, any cis-trans situation is a diastereomer, so that's another clue as well. Question 10. True or false? Both molecules are optically active. False. Alright, can you see why? So we solved the RNS for these earlier. But look, did you notice that both the front and back chiral centers have the same exact groups coming off? We've got OH, methyl, hydrogen, and the connecting carbon. Since the groups were the same among the chiral centers, and one is R and one is S, that molecule is a meso compound, meaning it is achiral overall and thus not optically active. Now, what about the one on the right? It also has equal groups on the chiral centers, but its chiral centers are not opposite, so they don't cancel out. Thus, that one is still chiral overall, meaning that one on the right is optically active, not both. And that's all the questions. You made it through another review. And of course, if you need more help, you are always welcome to drop a comment or check out my other videos. For now, hope this helped, and I will see you around.